Okay, analyze this truss by the method of joints. Okay, so I have what looks like it would be a Pratt truss. We'd call it a Pratt truss if there were actually uh, members between C and D. So imagine a member in here and another member in here. And imagine a vertical member like this. So if it had such members, we would have a Pratt truss. It would be a Howe truss if it had these missing members, but the cross members were sloping in the other direction. Okay, so if you look up Pratt truss and Howe truss, you can see how they would look similar to this. So I probably wouldn't consider this to be neither a Pratt nor a Howe truss because it's missing those three members. So it's not the best design, but nevertheless, I want to analyze this by the method of joints. Okay, notice I've got some loads on here, 8 kilonewtons at G, 12 at H, 3 kilonewtons to the right at E. Well, the first thing I have to do is find the external reactions. There's a pin at A and a roller at both I and F. At A there's two reactions, at I and F there's two vertical reactions. Obviously by inspection A sub x has to be 3. The sum of the forces in the x direction is 0. But I challenge you to try to find A sub y, I sub y, and F sub y using the other equations of equilibrium, sum of the forces in the y direction, the sum of the moments about any point. There would be too many unknowns. So the trick to this one is that I have to break it at H. Imagine that there's an internal hinge at H, and I'm going to break this into two parts. So that's what I do here. I say break it at internal hinge H. Now be careful what happens here where I break it. Okay, the original drawing. Notice that there's a vertical load at H, 12 kilonewtons. And when I break it, I can choose to put the 12 kilonewtons on this side, the left analysis, or I could have put it over here, but don't double dip. Don't put it in both places. So in this case, I'm putting the 12 kilonewtons, I'm associating that with the left half of this truss. So I'll do two separate analyses, one based on the left and one based on the right. So as I analyze the left side of this truss, I've drawn the free body diagram. Obviously, h sub x is equal to 3 by taking the sum of the forces in the x direction, so I write 3 on here. Now if I take the sum of the forces in the y direction, it seems to me as though there would be too many unknowns, wouldn't there be? I'd have both a sub y and h sub y. What if I take the sum of the moments about point A? I can use that to find h sub y, so that's what I'll do, find the sum of the moments about point A. So I find the sum of the moments about point A. Okay, consider counterclockwise positive. H sub y times 10, the h sub y here, times the moment arm 10, minus 8 times 5, that's this 8 times 5, minus 12 times 10, 12 times the moment arm 10. I solve for h sub y and I find that it's 16 kilonewtons up. So I wrote it here on the figure, 16. So what's the unknown here, a sub y? So find the sum of the forces in the y direction, and then that'll enable me to find what a sub y is. So I find the sum of the forces in the y direction. I find that a sub y is 4, so I write it in here on the figure. Okay, so now I know what a sub y is. Okay, so go back to my original drawing. I know what a sub y is. Can I find I sub y and f sub y? I can take the sum of the moments about A now, of the entire truss, and from that I can determine the I sub y and the f sub y. So I write in a 4 on my original drawing. The 4 means A sub y, 4 kilonewtons. Okay, so now consider the entire truss, given that A sub y is 4, so I take the sum of the moments about point A is 0. So negative 8 times 5. Okay, so remember, it's the moments about point A. So negative 8, that's the 8 going down, times moment arm 5, minus 12 times 10, minus 12, moment arm 10, plus I sub y times 15, I sub y going up, moment arm 15, plus f sub y times 20, so f sub y here, moment arm 20, minus 3 times 5. Okay, don't forget about this horizontal load, and the moment arm is 3. Okay, so I have too many unknowns here. I've got one equation and two unknowns. So am I helpless? Well, now I'm going to take the sum of the forces in the y direction of the entire truss. So I find the sum of the forces in the y direction. 4 minus 8 minus 12. Okay, this 4 is going up, 8 coming down, 12 coming down, plus I sub y, f sub y, I sub y going up, f sub y going up. So I have a second equation, I sub y plus f sub y is 16. Two equations and two unknowns, so now I'll solve those for I sub y and f sub y. And now solving the two equations simultaneously, I find I sub y is 29 going up, f sub y is 13 going down. This is redundant, having both a negative and a down arrow. I guess I could do it one way or the other, so I could say 13 down, or I could just say negative 13. So let me go back to my figure. So I sub y is 29, so write a 29 here. F sub y is negative 13. I already drew the arrow pointing up, so I have to put the negative sign here. So F sub y negative 13. So at least I have the external reactions. Now I want to go back to the left side. So remember this figure. Okay, so get a good look at this. I'm going to analyze the left side, starting with joint H. So going back to analyzing the left side, okay, here's H. This is a 45-degree angle because if you remember the original drawing, it was 5 meters tall, and this dimension is 5 meters, so this will be 45 degrees. So get a good look at this. I've got 12 going down, 3 to the right, 16 up. So I reproduce joint H here. So I could find the sum of the forces in the y direction. That would leave me with only one unknown, F sub hc. Okay, I forgot about the 12 kilonewtons pointing down, so I fixed it. Okay, F sub hc sine 45, that's the vertical component of this vector, plus 16, so the 16 going up. And then I could say minus 12 is equal to 0. I can't erase pen, I just crossed it off. I'm not redrawing the whole joint. Okay, so I say is equal to 12. So I've got these two going up, this is going down. So what I find is F sub hc is negative 4 square root of 2 kilonewtons. So I'll write that on the figure, and then I'll find the sum of the forces in the x direction, which you see right here. F sub hc is negative 4 square root of 2. Now take the sum of the forces in the x direction for this joint. Negative F sub hc cosine 45, horizontal component of this vector, which I just found, minus F sub hg, the only unknown in this equation. Substitute in the appropriate values. F sub hg is 7, so this right here, 7. Okay, so that does it for joint H. Okay, where am I? Okay, go back to this figure. Okay, I'm still working on the left. Actually, let me use this other figure I drew. Okay, this figure. So I know F sub hc, I know F sub hg, so I'll write those on the figure. F sub ch or hc, negative 4 square root of 2. That represents the bar force. And then in hg, or gh, that will be 7. So I'll put a 7 here. Alright, how was that so far? So why don't I move on to joint C? At joint C there's two unknowns, so I'll analyze that next. So take joint C off to the side, like I have here. Okay, how was this? So a pretty simple calculation. Find the sum of the forces in the x direction being 0. F sub CB is negative 4. The sum of the forces in the y direction for this joint equal to 0, so F sub CG is 4. So I'm going to write those on the drawing. Okay, so what do I have here? F sub CB is negative 4. So this will be negative 4 right here. And then F sub CG is 4. So that'll be 4 right here. Okay, so what bar forces do I still need? Take a look at joint A. You can determine by inspection of joint A that if you have 4 going up, then there must be 4 going down, meaning that bar BA would be in compression, wouldn't it be? So I'd actually have -4 in bar AB or BA. That's just by inspection. Inspect joint A. And same thing in the x direction. If I've got 3 that's pulling out in this direction, that must mean that there's a tension in bar AG of 3 kilonewtons. So just write 3 here. So those are just by inspection. Okay, so what's still unknown? Bar BG. So how do I analyze bar BG? Which joints should I analyze? Joint B or joint G? Why don't I analyze joint G? So here's joint G. Okay, I take the sum of the forces in the x direction is equal to 0. 4 going up, FGB, sine 45, that's the vertical component of this one. Minus 8. Be careful, it's very easy to miss that 8. Now remember that at joint G, we've got that 8 going down. So I find that f sub GB is 4 square root of 2. So I'm going to draw that on here. Okay, so I guess I don't need to find the sum of the forces in the y direction. I made a typo here, didn't I? I think I want this to be f sub y. Okay, I'm not going back and fixing it. So I mean f sub y here. Okay, now it's correct. So do I have to find the sum of the forces in the x direction? Do I really need to? Well, probably not, but I can use it to check my answer. To verify that 4 square root of 2. If you make one arithmetic error, it ruins everything, so it doesn't hurt to check the sum of the forces in the x direction to make sure that's correct. So finding the sum of the forces in the x direction is equal to 0. -4 square root of 2 cosine 45, that's the horizontal component of this one, the one I just found. -3 plus 7 is equal to 0. It is equal to 0. The left-hand side of the equation is equal to 0. The right-hand side has to be 0 for equilibrium. So I'm going to go back to my figure and write the value of FGB on there. So F sub GB, that's the bar force here. What is that, 4 square root of 2? Okay, how's that? So I think I know all the bar forces in the left side, don't I? Did I ever analyze joint B? Why don't I do that as one more check to make sure that B is in equilibrium, because I haven't analyzed it, so I'll analyze it now to check BA, BC, and BG. Okay, so I analyzed joint B. Okay, here's joint B. Okay, 3 bars feeding into that, so I'm showing them here. And I'm showing them in their proper orientations because I think I know which direction they're going in, assuming I didn't make any mistakes. Sum of the forces in the x direction is 0. Does it work? 4 to the left, 4 square root of 2 cosine 45, that's the horizontal component of this one, equal to 0. You can verify that that does work. Similarly for the y direction. So I say, aha. That means I probably didn't make any mistakes in finding these bar forces. So I'm done with the left side of this. Okay, so here was my analysis. Do I have all the bar forces? So now I'll move on to the right side of this truss analysis. Okay, so I'll analyze the right portion of the original truss. So remember this drawing from earlier, I broke the truss into a left portion and a right portion. I already analyzed the left portion, so now I'm going to analyze this portion, the right portion, so I redraw it, like so. Okay, so I verify the external reactions that I found previously. Remember, I found the I sub y and the f sub y previously, so I can actually verify that, which is what I'm doing here. I'm verifying that the sum of the moments about point I is 0, and the sum of the forces in the y direction is 0. Obviously, the sum of the forces in the x direction is 0. So this is just me verifying that the right portion of the truss is in equilibrium, as is the entire truss. So the first thing I'm going to do here is analyze joint F. Joint F. And now when I analyze joint F, joint F right here. Do I really even need to pull that out and analyze it as a separate free body diagram? So I've got F sub y is negative 13, meaning it actually points down. So I'm pulling down at joint F. That means I'll be pulling up in the member. So what does that say? That means that the member must be in tension, mustn't it be? Okay, so by inspection, I can tell you that F sub Fe is positive 13. Okay, without even drawing a free body diagram, I can tell you that it's 13 just by summing the forces in the y direction. Now what about if I sum the forces in the x direction, just for joint F? Okay, there's no horizontal load on F, so that'll be 0. So bar IF is a 0 force member. So just by inspection, I can tell you what the force in members FE and FI are. So and now why don't I analyze joint E? That'll be a little more challenging. So I will draw a free body diagram of joint E. Okay, joint E. Okay, I've isolated joint E here. I've got 3 kilonewtons to the right, 3 bars that feed into it. Joint E, and I already know what the force in member EF is. It's 13 in tension, so I have that listed here. So I'll find the sum of the forces in the x direction, the sum of the forces in the y direction. I'll have 2 equations and 2 unknowns. So I find the sum of the forces in the x direction. I wind up with what I call equation 3. Looks like I have too many unknowns, 2 unknowns in one equation. I probably should have found the sum of the forces in the y direction first, because I noticed that in the y direction I'll only have one unknown, that is F sub EI. So why don't I find the sum of the forces in the y direction, find what F sub EI is, and then stick it into equation 3. Okay, so I find the sum of the forces in the y direction right here. Negative F sub EI sine 45, that's the vertical component of this one, minus F sub EF, that's the 13 that's going straight down. I stick the 13 in there. Okay, and then I ran out of space. I'll come over here. Okay, so doing the algebra on this, I find that F sub EI is negative 13 square root of 2 kilonewtons. That's the exact answer. So that'll be this one right here. This is negative 13 square root of 2. Okay, so now I can take that figure, negative 13 square root of 2, and I can stick it back into equation 3. I'll put it right here. And that'll allow me to back out what the bar force in member ED is. And like magic, it gets done. So using equation 3, which you see up here, F sub ED plus the square root of 2 over 2, stick in what I just determined for F sub EI, is equal to 3. So solving this, I get F sub ED is 16 kilonewtons, so I know the bar force in ED, and I know what it is in EI. So let me write the 16 on here. So 16 right here. Here's 16 right here. Okay, F sub ED 16, F sub EI negative 13 square root of 2. I'm going to write those on my main figure. Okay, so here's my main figure for the right side. There was an original drawing that showed the whole truss. I'll bring that back at the end of the video. So F sub ED is 16. So right here I've got 16 in this member. And then EI negative 13 square root of 2. So that's in this member. Negative 13 square root of 2. Okay, how does that look so far? So which joint should I analyze next? I could use D, I could use I. Why don't I analyze joint D next? So what do I have at D? I have what look like 3 bars feeding into D, node D. So I'll be able to figure out what the bar forces in DH and DI are. So analyzing joint D, which is what you see here, 2 unknown bar forces. So I find the sum of the forces in the x direction for this joint. I find that the force in member DH is 16 square root of 2 kilonewtons. So I can write that on here. (16 square root of 2). There you have it. And I'll find the sum of the forces in the y direction to find F sub DI. And finding the sum of the forces in the y direction, as you can see here, I find that the force in bar DI is 16 kilonewtons in compression, so 16 here. Okay, so that gives me two more bar forces that I'll put on my diagram. Okay, so going back to this illustration, the force in member DH, 16 square root of 2. Square root of 2 in tension, and then in DI, that's 16 in compression. Turn it sideways. DI, 16 in compression. Okay, how is that? Okay, now I can analyze joint I to find the force in member HI. So next I'll analyze joint I. Okay, for my diagram of joint D, make sure you put a negative in front of that 16. I think I forgot to put that a minute ago. I found that the force in member DI was 16 kilonewtons in compression, so F sub DI negative 16. But I did draw it correctly on the other diagram. Okay, so now analyzing joint I, right here. Okay, so this diagram where I've been drawing all the bar forces. Okay, notice I did put the negative here for DI. So I want to find the force in member HI. So F sub IH, HI or IH. Why don't I sum the forces in the x direction and set that equal to 0? Notice I don't show bar IF there. IF was a 0 bar, so I'm not bothering to show it in my free body diagram of that joint. Okay, so equilibrium in the x direction, that's what I'm doing here. I find that the force in member IH is 13 kilonewtons in compression. 13, so I'll draw that on the free body diagram. Negative 13. Okay, notice that the F sub ID, I know the direction, so I'm showing it in compression. Similarly with IE, I show it in compression. If I don't know the direction, I didn't know IH, so I assume tension. The fact that I get negative means it's in compression. Okay, so it looks as though I can't really, there's really nothing new to find using this free body diagram, but I can verify my figures by finding the sum of the forces in the y direction. So finding the sum of the forces in the y direction, as you see here, negative 16, that's going down, minus F sub EI sine 45, that's the vertical component of this one, plus 29 going up. Okay, substitute what I just found for IE. Actually, I found that a little while ago, F sub IE, plus 29, perhaps equal to 0, that's what I'm checking here. So I find that equilibrium in the y direction is satisfied. It is satisfied. So this calculation doesn't give me any new information, but it does verify my previously determined numbers. So from this, I determined what F sub IH was. So let me go back to this drawing. So in the bar HI, I've got 13 kilonewtons in compression. Okay, how is that? So I think I have everything, don't I? I have every bar force. Why don't I check joint H just to verify? I haven't examined joint H, so now I'm going to examine the equilibrium of joint H just to verify everything. Examine joint H and make sure that it's in equilibrium. So I've drawn a free body diagram of joint H based upon the external loads. Actually, not external loads. Those are the loads from the left side of the truss, aren't they? That was the H sub Y, and this is the H sub X. So those are actually the reactions from the left portion of the truss, which I analyze separately. And then I've got the internal member forces here and here. So is this in fact true? I challenge you to do the math, and you'll find that it is in equilibrium in the x direction, it is in equilibrium in the y direction. And now for my final act, I go back to the original truss drawing, the free body diagram of the whole thing, and I show the member forces, the bar forces, on every member. As you can see here, the negative means it's in compression, positive means tension. So there you have it.